All right, guys. So let's go ahead and get started. So we're just going to go over a quick review really quickly of some of the stuff we talked about yesterday. So somebody tell me really quickly what gravity is. Somebody? Yeah. Yeah, it's like a force, right? And it's a force of attraction between two objects, right? Is that what you're going to say, Ava? Right, well, so it comes from the center of the objects, right? And so between any two objects, there will be that force of attraction. And basically, the two factors that affect gravity are the distance between the two objects and then their mass. So there's a lot of mass, going to be a lot of gravitational force. But if they're really far apart, that gravitational force decreases as they move apart. Okay, that was all yesterday. Now, let's move into more what we're going to talk about today. Well, before we do that, are there any questions about that? Or are we all good with that? Okay. All right. So let's move on to more like our implications. Okay. And before we do that, I want to go back and just kind of cover some stuff. This is a little bit more in depth than what we talked about yesterday. And we're going to talk about a little bit of history too, of like where the force of gravity comes from. Right now, the force of gravity is just a thing, right? It's not like we made it up. Okay. We just kind of discovered it. And more importantly, we discovered like how to calculate it. Okay. So like we just said, gravity is this force that keeps the Earth in orbit around the sun, right? It keeps us on Earth. Pretty much everything in the universe is affected by gravity in some way or another. And it was, I'm going to use the word discovered, okay, not invented, discovered in the 1600s by an English scientist named Isaac Newton. Has anyone ever heard of Isaac Newton? Pretty much everybody in here, right? And you all know about the apple hitting him on the head, supposedly. Okay, good. So we all know kind of the basic story. So pretty much he has this revelation about gravitational forces and things like that, right? And he takes it a step further and says that the same forces that are acting on Earth, like these gravitational forces that cause objects to fall, they're also happening out in space. And this is like a big revelation because at the time, in the 1600s, people weren't really thinking about space in the same way we think about it. Like we think about it like we know the moon is there and all the different planets in the solar system and the galaxies and other stars, right? We know all that. Back then, they didn't know really a whole lot about space, like as far as the average person didn't. And even like the scientists of the age were still kind of figuring out some of these universal laws, right? Like they didn't know, for one thing, they didn't really know what was causing like the planets to orbit around the sun and things like that, right? That is until Newton comes up with this idea of gravity, and then he says, well, this gravity must extend out beyond Earth to out into space as well. And so this force of attraction must be what causes the planets to go around. And now remember, he's also the same guy that comes up with the laws of motion as well, right? Newton's 3 laws of motion. So it makes sense that the same guy who's already thinking about motions of objects and things like that would also come up with this idea of gravity, right? Like it's all kind of in the same wheelhouse, okay? So just remember, gravitational forces can be described as a push and a pull. You're either like you can be pushing something away or pulling something, right? The way we experience gravity is where we're being pulled, right? But you could also think about it as like a push from above, okay? But either way, gravity is what keeps us on the Earth, right? It's what keeps the Earth in orbit around the sun. It's what keeps the moon in orbit around the Earth. All these things are affected by gravity. Okay, so like we just said, Newton hypothesizes. Somebody really quickly just remind me what a hypothesis is. Skylar. Best guess. What you thinking? Jolie Ray, help him out.
A theory?
Kind of. Now, using that term theory in science gets a little confusing, right? Because we also use the word theory to mean something. Somebody get maybe a better, describe it in a better way. Elijah. Right. It's like a prediction of a particular set of things, right? So like traditionally, when you set up an experiment, you observe something and then based on those observations, you come up with a hypothesis, which is like what you think is going to happen or why you think something is happening, some phenomenon, why you think it's happening, and then you would test your hypothesis, and then based on whether your hypothesis was true or false, you can, write, like a theory would be like if your hypothesis was proved true time and time again over multiple experiments, then you could say, okay, we're going to move, a hypothesis into more of like the theory territory. Now, traditionally, like just in normal slang talk, we use theory just like normal, right? Like it's like an idea or, I have a theory about this. But just remember, in science, theory has a completely different definition, okay? All right, so let's keep going. So Newton hypothesizes, or he has this prediction or this idea that the same force that pulls the moon towards the earth also pulls apples to the ground and when they fall from a tree. So this is kind of this first idea of like a universal force or universal law. Okay, and so, of course, he calls it his universal law of gravitation. And basically, that just states that every object in the universe attracts every other object, and that force of attraction is just dependent on those two things we talked about earlier, right? Which is the size or the mass of the objects, and then the distances apart, right? So, like, technically, like we're attracted to the tables or like the chairs, okay? But that force is so much weaker than the force between the earth and us that we only feel the force of gravity pulling us down, right? Like we don't feel attracted to the wall. We're just pulled to the wall because the force of gravity from earth is pulling us down at a much greater force, right? Because the earth is so much bigger, okay? Did you have a question? Yeah.
So if the table and me was in space, I would be like a little bit pulled to the table.
Yeah, you would be a little bit pulled to the table, right? For sure, but it might take a really long. Number one, if there was like no gravity acting on you at all, it would take a really long time for you to be pulled to the table. Okay, that's number one, because your masses are so small, right? And then number two, we know that, and this is a good question to ask because it's leading us into our next point. But basically, we know that when you go out into space, gravity is still there, right? So even if you were out in space, okay, unless you were in an orbit, which we're going to talk about in just a second, you would be pulled back to Earth. Unless you were really, really far away, and then you really would be just kind of floating out. But even if you were away from Earth, you would still be attracted to the sun, right? So if you had like no motion or anything, you would eventually just be pulled into the sun because the sun is so massive, right? You would have to go all the way outside the solar system to no longer be affected by the force of gravity from the sun because that's just how big it is, right? So that's a good kind of continuing point here. So basically when we're out in space, gravity is still there. I know that's kind of like a misconception. You go to space, you're now weightless, right? You're no longer affected by gravity. Okay, but you definitely are. Gravity is still a force, right? If gravity didn't work in space, the Earth would just fly off from the sun, right? Gravity obviously still works because the Earth is moving around. The reason astronauts appear weightless in space is because they're in what's called an orbit. Okay, they're in what's called an orbit. So essentially what an orbit is when you go up there, you're way above the surface of the Earth, right? And you're moving. If you were just standing still, you would fall back, right? But we know in the rocket ship when they lift off, they're going really, really fast. And by the time they get to space, they actually turn the spacecraft horizontal so that they can go really, really fast in like a sideways motion, okay? And what that's doing is basically they're falling, but they're falling like as they're going horizontally. And they get to going so fast that actually before they would fall back to Earth, they're actually already, past the curvature of the Earth, right? Because the Earth is a sphere. So before they would actually hit the edge of the atmosphere, they've already gone around. That's just how fast they're moving. Okay, it's kind of like, I should have grabbed one of these from the back, but if you have a ball on a string and I hold up the ball, right, and then I were to drop it, Gravity would just pull it down. But if I sling the ball and the string around, what happens to the ball and the string? Right, they stay. That's a perfect example. Here, can I have that really quickly? Okay, so Ava just did this whenever I was just saying that. She was playing with her bracelet. So like, look, if I hold the little bracelet here, it just falls, right? Does everyone see that? So like I hold it up, it falls. Okay, but then if I like put it on my finger and do that, see how it's like resisting the force of gravity due to its motion. Okay, here you go, Ava. So the same principle applies in space, right? If you go out into space, you will fall back to Earth unless you have what's called an orbit, right? And in order to have an orbit, you have to go really, really fast. Now, what is something, we've talked a lot about gravity, okay, but now we're getting into space, and so there's a distinct difference between on Earth how things fall and in space how things fall. What do you think could affect how things fall on Earth and in space? I'll give you a hint. This thing helps us stay alive. Without it, we would die. Oxygen, okay, yeah. What is oxygen a part of? The atmosphere, right? So the atmosphere changes how things fall. How does it change how things fall? Like on Earth. It's not as what? Okay, yeah, so the atmosphere is very thick, and then you go to space and it's not very thick, okay? So really quickly, let's just talk about like how would the atmosphere potentially cause two objects to fall at different rates? Because like we know when we talked yesterday that the force of gravity is always the same on Earth, right? It's about 9.8 meters per second. That means if I drop any object, it should, in theory, fall at 9.8 meters per second. But we know that that doesn't always happen because we've dropped things before and they either fall faster or slower. So why do we think that is? It's not. I know it sounds like it would be because of their mass. It's actually not because of the mass. What is it? Air resistance, okay? It's due to air resistance. And I'm going to show this point actually right here. So, all right, so I have a piece of paper and I have a textbook. All right, now, which one of these has more mass? The textbook, obviously, right? Okay, now if I drop these two things side by side, which one is going to hit first? The textbook. Why? Because air resistance. I know it's really tempting to say because it has more mass, right? That was kind of where I was leading you, but I may have led you astray there. It's because of air resistance, believe it or not. And I can actually demonstrate this. So if we drop this, okay, do you see how slow the paper falls, right? And if we drop the textbook, okay, very quickly, right? Sorry if that was a little loud. All right, but what if we had some way to take away the air resistance of the paper? What do you think would happen? Yeah. The paper would fall faster? If you took away the air resistance, the paper would fall faster? That's right, yeah, because right now the paper falls very slowly. Okay, if we were to take that away, obviously it would fall much faster. Now, there's no way I can take away all the air resistance, right? Because in order to do that, I would have to pull all the atmosphere out of the classroom, and that wouldn't be very good for all of us in here, right? So I'm going to do something closer, and what I'm going to do is we're going to have basically the same air resistance for both of these objects. So when I drop this book, there's a certain amount of air resistance that is just due to the shape of the book, right? When I drop it, it's going to displace a certain amount of air. But the whole idea here is that these objects under normal or without air resistance, these objects should fall at the same rate, right? So what I'm going to do is I'm going to make these where they share the same air resistance. And what we're going to see is they should fall at the same rate. So what I'm going to do is basically put the piece of paper on top of the textbook. Now when I drop it, the textbook is removing the air resistance, right? So both of these objects will be, essentially experiencing the same amount of air resistance. And so what we see is they fall at the same rate. So did everyone see that? I'll do it one more time. I have my paper here. I have my textbook here. All I'm doing is putting the paper on top of the textbook, dropping it, and now they're falling at the same rate. Okay, now this rate, I can go ahead and tell you, is going to be slightly slower than 9.8 meters per second. Why is it slightly slower? Air resistance. One more time, just to make sure we all got it. Yes, it's due to air resistance, right? Nothing on Earth is going to fall at 9.8 meters per second exactly, because you could drop anything and it's going to have some amount of air resistance to it. Now, how could we possibly make something, fall as close to 9.8 meters per second as we possibly could? But if we put it higher up, won't it still experience air resistance on the way down? Okay, so maybe not higher up. We could make the air thicker where? In the sky. But wouldn't that mean it experiences more air resistance if the air is thicker? Yeah. Yeah, so if we could put everything in a vacuum, then yeah, we could remove air resistance, but that's kind of like not realistic, right? Because how would you remove all the atmosphere from Earth? Okay, think about the shape of the object. What are some ways we could potentially make an object fall as close to 9.8 as possible?
Something like a paper airplane.
Okay, what about a paper airplane makes it really good at flying? The wings, right? And not just the wings, but it's the particular shape. Right? If I drop this piece of paper, it's going to fall very quickly. But if I ball this piece of paper up so that it's not displacing as much air, it's going to fall much quicker. All right, so, yes, basically this all boils down to air resistance. Okay, now that's on Earth. What happens when we get to space? Is there any atmosphere in space? No, so things get a little different, right? We're no longer dealing with this air resistance, and in fact, let me go back and I will just show you a demonstration of this. So, there it goes. Oh, wrong one. Well, we'll keep going. Well, I'll show it to you later. Basically, the demonstration was these two astronauts, it was during Apollo 15, they had the Falcon feather and they had a hammer, and of course on the moon, there's no atmosphere. They dropped both land at the same time, okay? Because they're experiencing the same gravity. Now, this is an important idea here. On the moon, is the force of gravity 9.8 meters per second? No. Why? Because why? Right, the moon has less mass. And so because the moon has less mass, therefore it's not going to have the same pull, right? It's going to have slightly less pull. So in fact, when you go to the moon, you actually weigh about 1/6 what you weigh on Earth, right? Because the force of gravity is different. Okay, now your mass doesn't change. Your mass stays the same, but how much you weigh, or basically a percent, or basically a calculation of your mass times the force pulling you down, right? Because that force is changing, your weight changes. Okay? All right. Now, let's move on.